Welcome. In this session, I'm going to define the concept of average value of a function. In some sense, this is a special case of the concept of mean of a random variable you see in statistics, but we are going to look at it in a much more mundane way, thinking of it as defining the average of something that is continuously varying over time. For example, average temperature over a day. In the old days, they used to just take average of the minimum and maximum for the day. This is kind of rough because if the temperature changes suddenly near the beginning or end of the day, it gives a wrong impression of what the average was. A better way to do that would be to measure the temperature each hour, for example, and then average them, or maybe even more frequently. So it's a question of practicality. Mathematically, we don't need to worry about that. Just think about the quantity we are averaging as a continuous function. So we take the value over several places and then average them. So if I take n places, then I evaluate the function at those n numbers and average them. Take the total, divide by n. So it looks like this. Take the value at this n locations selected, total, divide by n. I'm going to rewrite it a little bit by multiplying inside the braces by b minus a and then dividing outside by b minus a. It doesn't change anything. But now the quantity inside the braces looks like a Riemann sum because b minus a over n is the width of n equally spaced intervals. And we'll make the simplifying assumption that all these quantities are selected in those intervals, so they're more or less evenly spaced. Then I have a Riemann sum divided by width of the interval. So if I increase the number of locations I pick, or instants I pick, then I get in the limit the Riemann integral, the definite integral, divided by width of the interval. So this leads us to give the definition of the average value of a function over an interval as the integral divided by the width of the interval. It's also a way to think about this geometrically, which I will explain after doing an example. Let's find the average value of square root of 1 plus x between 0 and 3. So if we just apply the definition, width of this interval is 3 minus 0 or 3, so we take 1 over that, times the integral of this function over that interval. So integral from 0 to 3 of square root of 1 plus x. That's 1 plus x to the power 1/2. To do the actual integration, I need to find the antiderivative, which I'm going to do using the substitution u equals 1 plus x. I get du equals dx, u to the 1/2 du. By the power rule, the antiderivative is u to the 3/2 over 3/2 plus c. Simplify this a little bit. Dividing by 3/2 is multiplying by 2/3, and then go back to the original variable. I get an antiderivative as 2/3 1 plus x to the power 3/2. And the fundamental theorem, the definite integral is the net change between 0 and 3. So I have this integral equals the quantity inside the braces and then the net change times 1 over 3. Now it's just an evaluation. Plug in 3 and 0 and subtract. And if I just combine the two fractions, 1/3 times 2/3 is 2/9. And if you do the calculation, you will get 14/9. So the average value is 14/9. To think about this is that if I take a bar graph with uniforms with bars, the average height of the bars is the total area of all the bars divided by the total width. Same reason as before when we did it algebraically. Area of each bar is height times width. So area of all the bars is the total height times width of each bar, which we assume is all the same, divided by number of bars, that's n. Or width of a single bar times n is the total width of all the bars. So the average height is total area divided by the total width. In the limit, area of the bars becomes area of the region under the graph. So I get average height as area divided by the width, and that's precisely what this is. Area is the integral, this is the width, area divided by the width is the average value.